Okay. Last class we started learning about the inductive type of transducers. In the inductive type, I already told you there are two. One is called variable reluctance. The other one is LVDT. Okay. I also told you that LVDT type of displacement sensors are quite popular. You can design an LVDT to sense linear displacement as well as angular displacement. Similarly, variable reluctance type sensor also can be designed so that it can sense. But if you look at the comparison of these two, this is normally small distances or small angles. Because we saw that the G plus or minus delta G has to be small. Delta G by G itself has to be small, right? Because here air gap varies. Air gap is the one that varies. So I have delta by G must be small. So G itself is small and delta G has to be much smaller than delta G. So if you look at the available type of variable reluctance type of transducers, they are not more than 1 or 2 millimeters in displacement as well as 10 degrees in angle, if you're talking about angular displacement sensors. On the other hand, LVDT can be really small to large, very large displacement. Also, you can design an LVDT and use. The size can be, depending on the application, you can actually manufacture LVDTs for different sizes, right? So we can start from, this is few millimeters, to even 1 meter, right? You can design an LVDT. Now we look at one application of variable reluctance transducer. In a variable reluctance, if you look at the transducer made of copper wire, that's a coil, and soft ferromagnetic iron core. Of course, I put iron, but normally it's either silicon steel or nickel iron or some combination of iron plus other materials, basically soft ferromagnetic material. Okay, so it could be even ferrite. Okay, so the biggest advantage of a variable reluctance transducer is that it has a very long life. Nothing will. There are transformers which are made 100 years ago. They are still working because as long as you ensure that the work environment does not degrade the copper nor degrade the iron. In fact, we can now choose special irons which can handle, right? There are magnetic stainless steels, right? That do not rust. So we can have a very long life. So the variable reluctance type transducers, uh, as we have already seen, as a very nonlinear characteristics, because the output is not only proportional to delta G by G, it is proportional to delta G by G. Uh, if I use push-pull, whole cube, delta G by G whole power 5, and so on, right? So the best you can get is 1 or 2% non-linearity. Better than that would be, even to get 1 or 2%, you'll have to do a lot of design optimization. So, so this has inherently non-linear characteristics. Okay, so you will not see commercially for normal commercial applications, right? You will not see a variable reluctance type transducer at all. But there are situations where no other transducer will work. Okay. Uh, for example, I want to make a transducer which I want 25 to 50 years of shelf life, which means I make the transducer, I keep it up uh, without doing anything. I take it after 25 years, I switch it on, it should work, right? So we call this as shelf life. Then overload factor. We have already learned what is overload factor. Uh, Overload factor is nothing but uh, if you apply excess voltage over and above the range of the transducer should not get spoiled. So if you want an overload factor of 2 itself is very difficult, but if I want an overload factor of 20, then it's nearly impossible to design with any other type of transducers, right? And only variable reluctance will take that kind of abuse, I would say, and will still work. Even if let's say I make a transducer with a full scale of 100, so even if I apply 2000, whatever units, arbitrary units, right? Let's say to 100 kilopascal, right? I design, or 100 megapascal, I put 2000 megapascal, right? So I put this as a pressure sensor. Uh, it will still work, okay? So the it should still work. That's the, so we can design that very easily using variable reluctance type of sensor. Now I am going to show a video. Uh, you will see that this video is nothing but what is known as a battery of rockets. So you have something like 20 to 100 rockets mounted on a truck, and the rockets have to be fired from the storage itself, right? So if you have, let's say, you have one rocket, right, and another rocket stored next to each other, and if this rocket fires, the probability that it will ignite the rocket next to it is very, very high. So what do? We have to make a battery of rockets, because you can't take one by one and fire. You will see in the video that I'm going to show later after I finish this, that the rockets are fired in succession, sometimes even one every 50 milliseconds or 20 milliseconds, right? That kind of rapid firing. Uh, So what can we do? We cannot make the rocket kick off. So what is done is you put a rocket and right, and at the end you put an air tank, just simple air, right, and put a valve and put very large pressure, typically 400 bar, right? So 40 megapascal, okay. Uh, and then when you want to fire, you release the valve. What will happen? The air will come out as a jet, and the rocket rocket will move away, right? It will start moving because of the air jet, and when it clears certain distance from the storage, you fire the rocket. Right? You fire the rocket. Okay, so maybe 2 meters, 2.5 meters, and so on. Okay, so the problem now is, okay, this we can do, but what happens if there is a leakage? You are just going to make the rocket and store, and only when a war comes you are going to use the rocket. So you are going to store it, and the storage you can lose the pressure. So what happens if there is not enough air inside the air bottle? Then the rocket will not clear with the whatever distance you want, and it will start firing maybe very close to the other rockets, and you will have a fiasco. So what do? You put a pressure sensor here, right? And you ensure that if the pressure is greater than, let's say, 300 bar, then only the rocket will fire. Otherwise the rocket will not fire. You put a small control unit there, you give a firing command, and it will check if the air pressure is more than 300 bar only. Now such a pressure sensor needs to have very long shelf life, 25 to 50 years, right? And please remember, these are all going to be mounted on a military vehicle, so it may need to take 20 G of vibrations, because you don't know where you are going to transport these rockets, and it should have 20 to 40 G of shock. Okay. In terms of accuracy, I really don't need to. This need to be accuracy. Even a 5% accuracy is good enough, right? So if we have to design a pressure sensor like this, the only option is variable reluctance, right? I am going to show the video. Please watch the video carefully. You will see that the rockets get fired only after they leave the battery tank, right? It will not fire as soon as inside the battery itself. It will come out and then catch fire and start moving. Okay. So after the video, I will talk about the actual design of a variable reluctance type pressure sensor. Now we look at the variable reluctance type uh, pressure transducer design. Of course, this we have gone through this active, passive. So different type of pressure sensors. You have what is known as reaction type. You have a bellow that would expand or contract depending upon the pressure. So you look at the movement delta x, that will be made proportional to L. There's a force balance type pressure sensor. You balance the pressure that you want to measure with another pressure, and this is normally used for calibration. It has very high accuracy, stability, and precision. Uh, so these are the ones that are available. We'll revisit them when I talk about pressure sensor. So the reaction type you have already seen: bellows, board-on tube, piezoelectric, diaphragm. Uh, there's in the diaphragm you have a clamp diaphragm and a corrugated diaphragm. Each has its own advantage and disadvantage. Uh, when we talk about pressure sensor, all pressure sensors have two ports, P1 and P2, and the way that you configure P1, P2, I say that we are measuring. Uh, if P1 is vacuum, then we have what are known as absolute pressure sensor. If you put P1 at 1 atmosphere, 100 kilonewton per meter square, normally 101 kilonewton per meter square, uh, then seal that pressure, right? Then it's called sealed gauge pressure sensor. Then you can keep P1 as open to atmosphere. So P2 will be measured with respect to P1, which means it's called open gauge pressure sensor. If you use both P1 and P2 and take the difference, uh, then you have differential uh, pressure transducer, right? Again, there are types of pressure sensors. Uh, there is something called dry type. Uh, if it is dry, you can't use it on liquids. If you have wet, you can use it on both gas as well as fluid. When you have differential, because you have two ports P1 and P2, so in a differential you can have a dry kind of pressure sensor, which means you cannot use liquids at all. Similarly, you can have wet. Both P1 and P2 can be either gas or liquid. The transducer will work. Then the third option is one will be wet and the other one will be dry. Or one port you can give both liquid and gas, but whereas the second port has to be only gas, right? Again, there are different types of pressure sensors in terms of response. Static pressure, which means not varying in time, very low frequency variation. Dynamic, you have both DC and medium frequency AC. Transient, you have very high frequency signals in your pressure. So again, you have different types of sensors which will suit one of these. Okay. So we look at the measurement of pressure using diaphragm. So if I have a diaphragm here, uh, right, this is called a clamp diaphragm, and if I have pressure P1 and P2 and P2 is greater than P1, right, here what we do is we take P2 greater than P1. So the diaphragm will deflect upwards by delta x, and that will be the curvature that you will get. And delta x, depending upon where you are, right, is given by this equation. And if you see this, once I design, A is fixed, R is fixed, right? Young's modulus E is fixed, T is fixed, even though it is T cube, everything is fixed. So what varies is only delta P. That is P1, delta P is nothing but P1 minus P2, right? or difference of P1 and P2. Okay, so we see that the displacement is linearly proportional to the uh, variation in difference in pressures P1 and P2. So the diaphragm type pressure sensor, very popular. Now I'll have to measure delta X. Please remember what the delta P does. It simply moves the diaphragm. So which means I should sense the diaphragm movement delta X, then only I can measure the pressure. Okay, so we have already seen different types of transduction principle for measuring delta X, right? We have already seen strain gauge, we have seen piezo resistive, we have not seen the piezoelectric, we have seen the LVDT, we will see the capacitor, right? We will see the capacitor later. Of course, LVDT also can be used to measure this displacement delta X, right? So how are we going to use this? Of course, this is a strain gauge type pressure sensor. So you have 4 gauges. Please, there are 2 in the inner circle, and there are 3 and 4, right? So I have 1, 2, 3, 4. There are 4 gauges here, right? And this is very popular. You can only dry wet, dry or wet dry only. You cannot get wet. Because wherever you fix on whatever side of the diaphragm you fix the strain gauge, you cannot have liquid, because the liquid will then interact with the strain gauge and you will not get an output. Now LVDT type, again this is available as a commercial vibration. It has very high sensitivity, static and low frequency applications, long life, only limited by the fatigue life of the diaphragm, but not as long as the one you can get from the variable reluctance, but still better than the strain gauge type. But the problem is, if the diaphragm vibrates, you will get a very lot of noise in the output. Right? Even if the diaphragm doesn't vibrate, the sensor enclosure vibrates, right? You will get uh, interference induced by the vibration. Now we come to capacitive type. Again, this is the diaphragm. So we have P1 here, we have P2 here, and the diaphragm moves. So there will be a capacitance between this conductor and this. Also there is another capacitor between this and this. So if this is increasing, this will decrease, right? So you have a push-pull capacitor. We will talk about these type of sensors. So this is a very good sensor, but there is one very important aspect. The pressure medium has to be electrically insulating. If it is a conductive fluid, you cannot use the pressure sensor, because that will simply short circuit all the capacitive plates, right? So there's one problem here, that now piezoelectric, we will learn about piezoelectric a little later. So you apply pressure and it generates a charge, and the charge becomes a voltage, and this is again quite popular. You can Google search Q-Light. There's a company that specializes on piezoelectric type of pressure sensors. Uh, Very nice for dynamic and transient application, not at all useful for static. Now piezo resistive, uh, again used in micro machine sensors, what is known as MEMS, right? and you can get very small size sensors, but the problem is it doesn't have large shelf life, right? Maybe 5 years or 10 years shelf life only you will get. Now we come to our variable reluctance sensor. Again we have a center diaphragm, right, which moves, deflects depending upon P1 minus P2, and what we do is we put two coils here, so that when the displacement G plus or minus X, here G minus or plus X, so we have already seen this in a different form, right? If you remember, I put this form so that we can easily understand, but this is also okay, right? I put this and say this is moving here, this will be D minus delta G, and this will move up, so this will be G plus delta. It's the same thing here, right? Okay. Now how do we measure? Uh, the examples that we are going to look at is quite large pressure, full scale pressure ranges. Let's say 1 megapascal to 100 megapascal, right? It should have 40 times overload capacity. If you vibrate it, nothing should happen to the output. Uh, 20 G per second shock. It has to be wet, should be able to handle corrosive and conductive fluids. Shelf life definitely more than 20 years, right? All this can be achieved only with variable reluctance type. Here if you see, everything is green, whereas if you look at piezoelectric, it doesn't work for vibration, it doesn't work for overload. Life is only 10 years. Strain gauge life is only 5 years. Capacitive, the vibration sensitivity and overload capability are poor, right? LVDT, uh, sensitive to vibration. Overload, of course, you can handle it, but only 10 year. So if you look at here, even though I put 25, we can even go to 50 years if you take care, right? So variable reluctance type has this particular characteristics, even though if you look at it, these T are really bad, right? If you look at the rest of the uh, pressure sensors, they're all good, but when it comes to PR, but because this is good, right? Niche applications, as I said, in military applications, we use this type of transducers. So why it gives such a good characteristic in terms of vibration isolation, in terms of shock, in terms of overload. It employs no critical chemical bonding adhesive, results in long shelf life. The diaphragm is operated near very low deflection to thickness ratio. So because of that, the fatigue and overloading effects are negligible. You can design a wet type transistor that can corrosive fluids, because what is this? What you have? You have only iron. So you choose an iron, a type of steel that is ferromagnetic as well as has the corrosion characteristics that you want. Okay. But what are the cons? It's highly nonlinear. Linearization is very essential. Accuracy almost inferior to all other type of pressure sensors. But as a overload capacity is good, recovery from overload is quite fast. Large mean time between failure. MTBF stands for mean time between failures. But which means if you manufacture, let's say 100 transducers, and one transducer fails in 5 years, the other fails in 25 years, the third one is 10 years, then you put all the mean values and calculate what is known as the mean time between failures. As I already said, shelf life, typically 25 years you can easily get. Okay, now we analyze. This I had already derived in the class, so I will go through it quickly, right? So the inductance is N square A by reluctance, right? n square A by reluctance, where reluctance is L by mu, right? Actually this is L by mu naught mu r, right? So mu naught mu r is what I have put it as mu. Okay, so then I can put Li by mu I plus G plus or minus x by mu naught. So this equation we have already seen. Now we have actually put the diaphragm. You have two cups. Please note this is a cross sectional view. I will actually show the pictures a little later, right? So we have the diaphragm at the middle, and we send P1 on one type of one side, P2 on the other side, and through this we put two coils, L1 and L2. So here I will get L1 plus or minus delta L1. Here I will get, this is wrong, minus or plus delta L2. If I have equal number of turns of coil and make everything ideal, we will have L1 equal to L2, right? Not a big problem. And this again we have derived in the class. Delta L by L is delta x by x by 1 plus L by x mu r, right, into 1 plus delta x by x whole square and so on. Okay, this we have already seen. This is the actual characteristics that we obtained. You can see that it's a very nonlinear one, but if I take only from here to here, right, I can see that it's not really that amount of nonlinearity, but we can use this range. And what happens? I am using only a small portion of the range. This range is overlap factor, right? So the pressure sensor will not break. It will have only nonlinear characteristics, but it will still withstand all this overload that I apply on the diaphragm. Okay, so now in the design we will have to select materials. What material I should select for this, right? The cup. So remember we wanted the corrosion resistance, so we chose what is known as 17pH4, right? But the problem is 17pH4 steel. pH stands for precipitation hardening. That is, it is hardened when it's precipitating, when it's still in semi-solid form. Okay, uh, so but I need mu r to be very large, at least 10,000. The solution is that we use both material, right? Wherever flux comes, I will use nickel ion. Wherever the port and other support comes, I use 17pH4 steel, right? Okay. So now our design slightly has changed. Please remember, we had only one cup. Now we have two cups. There is an outer cup. This is 17pH4 steel, and the inner E is nickel ion. So the coil is wound on the nickel ion core, and so the magnetic flux will flow like this, right? So that would flow only through the nickel ion, which has about 100,000 relative permeability. This has mu r equal to 80, and this has mu r equal to 10 power 5, 100,000, right? So we get both of the worlds, and if you look at it, I have already sort of put all the designs. So there is a center diaphragm I section, then there are these two cups, two E cups, and we put everything and put welding, right? Once we weld it, nothing will happen to this transducer because there's only copper and iron, right? And if you make the design sturdy enough, vibration will not alter anything. This is actual pieces that we made. So you can see that this is the diaphragm. This is the end cup, and you see these two are nickel ion, right? And these two are SS316 sheets to safeguard the copper coil, right? If I don't insulate the coil copper from the corrosive liquid, copper is a very simple metal, and it will react with corrosive liquids, and I will have no transducer port. So what we do is we put the cup inside, and we put the coil inside, and then we put the sealing SS316 sheet, and we do that on this side also. We put this inside this, we put this inside this, we put on top, and then the whole assembly is put, and you weld all around the place, right? You weld around the place. Okay. Now this is a completed capsule. You can see there is one coil on this side, there is one coil on the other side, and there is the pressure ports are here, P1 and P2, and it's completely sturdy, right? Now we come to signal conditioning. Basically, we have two coils whose inductance is going to vary in push-pull manner. When this goes down, okay, this has to be like this. This goes up, right? Uh, so it's no. This again we have seen, right? So there are several types of signal conditioning. Some I will go through very quickly. Uh, this is what is known as Bloom-Lane bridge. I have not taught you this. Generally, we do not use Bloom-Lane bridge in inductive sensors. Uh, we use Bloom-Lane bridge in capacitive sensors. So when I teach you about capacitive sensor, I'll talk about Bloom-Lane bridge. At the time, we will apply inductive transducers also at the time. Take the output of the bridge, amplify, and please remember you have to demodulate it. We use a phase sensitivity detector to demodulate, right, and get an output. Okay. The thing is, you need an oscillator. Uh, this is known as the VN bridge oscillator. The feedback enables amplitude to be stabilized. Um, I will talk about this again later in detail. Uh, Signal conditioning circuit, we have already seen the synchronous type phase sensitivity detector. So we get the output from the bridge or from the inductances, and put a PSD, and we will get an output V naught. Low pass filter. So this is known as a multiple feedback inverting type low pass filter. So if I give a DC here, I will get minus of DC here, but it's not a big problem. It's a good design. Again, I'm not going to go through this design. If you have taken an analog and digital circuits course, you will come across this. This is the first prototype we made on PCB. So you see, this is the instrumentation amplifier, INA, and this is the quad op amp, right? And this is the PST, AD630, right? Please go to Analog Devices website and find out what is AD630. You will see that it's a synchronous demodulator, which is nothing but a phase sensitive detector, and this is the same one, but miniaturized so that you can keep it inside the box, using all surface mount devices, right? This is SMT technology. So This is the final assembled one. You can see the pressure capsule here, and you see the PCBs for the signal conditioning. So you have the pressure port P1. This is a open gauge type of pressure sensor. One port is opened to atmosphere, and you have the electrical connection, right, connector. Now we did test. This is the actual test results. You can see that the input up to 80 bar, right, is quite linear, right. Non-linearity is about slightly less than 1%, but as I said, we really are not looking for very good accuracy or very good linearity in variable reluctance type of pressure sensor. Okay. Now we look at different type of signal conditioning circuit. So what I do is I put minus Ki and put a different instrumentation amplifier, and this is phase sensitive detector and low pass filter and output. Okay, so this again we tried, not really very good, but this one is the one that I again discussed in the class, right. You have the same thing, minus plus, right. So this is L1 plus delta L, this is L1 minus delta L, so I give minus V angle 0, this I give plus V angle 0, that's what you give here, minus V angle 0, so this must be connected, and this is plus V angle 0, and so these two inductances are in the capsule. Okay, so once again you get the output, use PSD and put the low pass filter. So this is the complete circuit diagram. This is the oscillator, VN bridge oscillator. Right, and the rest of the circuit was given here. TL064 is a quad op amp from Texas Instruments, has a very low power consumption and also has FET input, which means the input current is in terms of picoamperes, so you really don't have to worry about loading. So in fact, when we were designing and fabricating it, we had to undergo a lot of trouble. First issue is 17 pH4 steel. It's not that you can just go to the market and buy, right? And it's very difficult to get hold of that. Finally, I have to place on record my sincere thanks to a government of India company called Mishra Dhatu Niham, or simply called Midani, in Hyderabad. So they gave me the 17 pH4 steel and the nickel iron steel, right. SS316 is readily available. You can buy anything. Now to fix the coil inside, I needed 2mm Allen screws, right, and that was really difficult to source the 2mm Allen screws. Ultimately, I had to get it from Germany, right? And of course, to bring the terminals out, I need glass to metal seals. Not a problem. You can buy them. They are still easily available. Coils, of course, you can fabricate the coil, and you'll have to put everything. Please remember, if it has to, vibration should not affect. What you do is you fix everything, right? You put everything inside and pour epoxy and seal everything, right? And the last thing is welding. You need to weld the inner eye section and this cup and this cup, right? So the whole round and round you need weld. So welding, we tried initially MIG welding, TIG welding, nothing worked. What worked was electron beam welding, right? Electron beam welding machine. So once again, I am giving you the different views. This we have already seen. These are the parts. Uh, you assemble it, test it. Once everything works, you put everything inside, put a epoxy. But please remember, electronics, sometimes you need to adjust resistors or change something. Only those terminals you keep out, and put epoxy and seal everything, so that if you are putting 20 G vibration, nothing happens. This is the test setup. This is the pressure generator. This can generate up to 1000 bar, right? And this is the test PC. You can see the waveforms on the oscilloscope, what is the oscillator voltage, and we have already seen these are the PCBs. And so we finally made this work. If you go to Hyderabad and you are allowed to see the missile museum, uh, you can see one prototype of this transducer, saying that developed at IIT Madras. So this transducer is now manufactured by our defense, a company under Defense Research and Development Organization, and being used in several applications. So I'll stop here. I'll see you in the next class. Thank you.